Okay, let's start. So today we're going to talk about the mobile part for this application. So last week we kind of go through the three diagrams for browser extension, desktop app, and mobile app. The desktop app we have three components, which is the electron, the desktop UI, and Neo, which is the JavaScript to Rust. The right part, those two are the same across all those three different use cases. So the browser extension also has kind of has the same on the database on the far right and the middle layer. So for the mobile part, we have the iOS or Android app on the left. So that's the UI, that's the user interactive layer. The middle part is the core layer, which is in Rust, and the right part is the database. So today we're going to so today we're going to basically focus more on the Android part. So talk in a high level what it looks like. So if you go to the class website, we have links to Android and iOS. So those two links goes to the Rust library on Android. So what does that mean? That means we're talking about how this middle component works and how does the middle this core component and the database piece works and how it glue together the Android to the Rust. So here we see a bridge, a Rust bridge. So that's kind of the focus for today. So those two blogs are talking about Rust to Android, and another one is Rust to iOS. Who knows which language, which company is backing iOS? Is which company is iOS? Which company is okay, so which in terms of who owns the developer for Python? Try a guess. No, it's Google. So Google hired the Python creator. I think. Yes, it's used extensively. Who do you know a language called Go? Go, language called Go. Okay, so it's Go, which is also Google's language. So Google owns the developers, so they pay those developer salaries for developing the language. Who who is uh, um, who is a developer? Which company backing developer for Rust? Give you a hint. Close. Firefox is a product, is a browser. Yeah. So Mozilla is backing Rust. So that's why like this blog is you see it's actually Mozilla's blog. So it's talking about how you can using Rust on iOS, using Rust on Android. So those companies trying to develop a like an ecosystem for their languages. So in the past, do you know which company backing like C and C++ in the past? No idea. Where is used most? C and C++. Never heard of that? Okay. So those are like AT&Ts and in the old days, the communication companies. So all the infrastructures, like Bell Labs, C, C++, those kind of languages are developing in that age. So those larger companies, they kind of making standards, pay salaries for the developers for those languages. Good. Who knows which company pays developers for Java? Yeah, it used to be Sun. The Oracle bought Sun, so now it's Oracle pay. But now, like, because every those major languages, right, it becomes like a mainstream languages. Usually, you get those kind of industry support for from major companies, and they have their own agenda to push either their products or kind of control the standards for those ecosystems. Um, so Rust is like a new player. Mozilla is a new. Well, it's not a new. Do you know which product Mozilla is? Before Firefox, how many browsers there is? Which one is Mozilla's browser? Probably you never heard of it. You know that Netscape, something like that. So there are. So today we have Safari, we have Chrome, we have Edge, and we have before that we have Internet Explorer, and then before that, now before that there is Netscape and other browsers. So Mozilla used to be, if my memory is correct, but also develop a browser before Firefox. So long story short, those companies has kind of histories on those product and languages. They kind of coexist for a long time. So Rust is a language which is still in developing mode. Like it's not so mature as those mature language like Java or C++ or even Python or iOS. But it has a very unique feature is like it's safe in terms of C++ and C language are not safe. Safe means everybody know what safe means. Just in general sense. Dangerous. What does dangerous means? It's safe. Okay. Okay. That's very close. That's actually that's the answer. So if you write in I think so you guys learn like high level languages. You are using like Java or Python. You don't care really about how the computer memory works in a lower level detail. So when you create an object, let's say you create an array or create a string or you create some other things, you don't really destroy it after you use it. So that means like in Python or Java, those kind of high level languages, you use it and the garbage detection is embedded in the language itself. So when you don't use those objects, it goes away automatically. So developers don't worry about those garbage. But in terms of lower level language like C and C++, that's you create something, and if you don't use something, you need to explicitly say, I'm going to deallocate those objects. So if I create some structure and I'm using it, I do some updates to object to something. So basically, you are manipulating the one and zeros in the memory. Who knows what is memory? How much memory do you have on your computer? I'm talking about RAM. Yeah. Right. So So we all run a lot of programs, right? Our computers can run multiple programs, multiple applications at the same time. They all, everything you see, like on the screen or anything you do, it occupies some memory, which is the RAM. Like you see those characters on the screen, it must be mapped to some memory, actual one and zeros in your hardware, in your RAM. So for lower level languages like C and C++, you need to actually manage the allocation. When I say allocation, is the creation of those zero and ones and the deletion of those zero and ones. Otherwise, it's going to be just like appending all stuff into your memory and never get deleted, and you will be out of space. It's like you have a room, you just put in stuff in, you never clean it up and go into the garbage. The room is finally going to be occupied. So in terms of lower level language, the one most critical difference is you're going to manage the garbage yourself. That means you put stuff in, you're also going to explicitly manage how to delete them, how to remove those garbage. So there is a term like in Java and all those higher level languages, there's a term called garbage collection. What does that mean? Sort of, right? So you create something like you create an object or you create a string or you create anything, you create a space. You declare I need a space, I need 100, let's say I need 100 bytes in the memory, and I'm going to fill in the 100 bytes with a bunch of one and zeros. And afterwards, you need to explicitly say, I'm going to remove those 100 bytes. So those explicit remove 100 bytes is called garbage collection. So that part, if you're using Python or Java or higher level languages, you never actually see that part. You never actually see I'm going to explicitly delete the 100 bytes. But in languages like C and C++, you actually must do that. So what's the advantage of that? Explicitly manipulating memory objects. Like you explicitly control how many bytes you allocate, how many bytes. Um, so what's the advantage? You have the capability to do that. What's the opposite? What's the disadvantage? Allow you doing that. Which one is more safe? Which one is more dangerous? So give you those superpowers, right? Give you a superpower. You can delete anything in your. So now let's imagine, take a snapshot of your memory in the computer. If I give you a capability, you can delete anything for like within your memory. Is that more safe or is that more dangerous? Okay. Right. So that is more dangerous. And you give you superpowers, it's more dangerous because if now I'm give you like a magical power, you see, I'm just going to delete something, some one and zeros in my memory. What do you think your computer will do next second? You're probably going to crash, right? Why? Right. Right. So because that's a very good answer. So because our computer is very complex, but it's also a well structured system. It's like a biological you can see it's like a life. You can see it's kind of mimicking a very complex but well organized, structuralized, like a even like an animal or like a kind of like a biology system. You think that way. So it has layers and layers of each other. If you randomly start to cut something, or it's actually not as robust as a life. If you break a branch of a tree, usually the tree don't die, right? Because it has a yeah. But computer is actually in that sense actually more fragile than that because everything you see the computer like what it's doing, it's very rigid. It has it must be every one and zero in a lot of senses. It must be lining up at the exact boundary. So you cannot randomly change something. Sometimes it's if it's just some data, it's okay. Maybe you see like a picture with some random noise dots. Yeah. Yeah, your computer will crash because if you actually modify the computation instructions, it get a wrong instruction. Like if next instruction um, is saying I'm going to show this screen, but if you modify the instruction to something actually computer never understand, which has very high probability, it will just crash. So everything will stop. So it's actually a miracle to some extent that everything is working because all the structures, those kind of data structure, all are lining up. So in terms of Rust, right? It's back to the safe law. It's a safe language, like in a sense of you kind of combine the high level language to low level language, but also maintains the safe means it does more checks like Java and Python does for those data structures, but it also allows you to do those kind of system level, which is like C and C++ level memory manipulations. You can actually also try to do those unsafe operations. So it's a powerful language. Actually, it's like a new kind of a paradigm for the language to be able to bridge the gap between the high level language. You have more you work on a more higher level. You don't worry about those low level details. You have no chance of crash your system if you're using Python or Java. Actually, it's very hard you crash your system if you're writing everything syntax correctly, right? You can run some compute programs like malfunction or never or it's in an infinite loop, but it's very hard for you to crash your system because those languages handles the memory safety, like the allocate object for you, delete object for you, so you can get logic wrong, but you never mess up your system. Like you have very lower chance of mess up your system. But if you program in C and C++, you have very high chance by not deleting object you're not deleting, by not deleting the right part of those objects, low-level objects. If you, as Jason said, if you don't know what you're doing, you have high chance to get all sorts of system crashing because you deleting something or you change something which you have no idea what's going to happen. But that's the superpower. That's why. But because you're talking to the machines, all the operating system is built on those low-level languages. So Rust is like the new player, and it kind of bridges the high level and low level together. You can do both things and also do the safety for checking those objects. Anyway, so let's go back to the mobile and the Rust. So so those two blocks. So we're talking about this piece, this Rust and this mobile piece, right? So in mobile development, we have a different language. We have Java, like JVM or Kotlin. Okay. Not sure I'm pronouncing things right. We have Swift. We have to get this Rust bridge. So here, uh, follow the the blog. Basically, they're talking about you need Android SDK tools. You need some kind of NDK native developer kit. You need to do those kind of setup, and then you need to define some kind of target. And you see the targets has some kind of naming to it. They have architecture 64 Linux, they have ARM v7, they have i68.6. You have different architecture. Then you have AR, you have a linker, and then basically this is you need to set up your Rust to be able to add those targets. Then you can use the command cargo build to build those targets. So what does that mean? Any guesses? What does architecture means here? Any guesses? Like what does architecture 64 means? Like ARM means and 686 means. How many? What's the OS? When you see like is your OS a 32-bit system or 64-bit system? For Windows, when you buy it, what does it mean? When I say it's a 64-bit system versus it's a number, but what does that mean? What does it mean? Okay, that's very close. So, so which is better or which is more powerful? Right. So that means bytes. That means one and zero. That means bits actually. So bits is 1 bit is 10 or 1 byte or one byte is 8 bits. So bit is smallest one and zeros. So that actually corresponds to hardware to the memory chip, right? The smallest state on the hardware is 1 bit, is one and zeros. So 64 means every instruction the CPU is executing is going to in an approximate way is going to be able to manipulate 64 zeros and once. So in one cycle. So CPU is driven by a clock or some kind of cycle, right? It kind of every nanoseconds or even smaller time intervals, it's trying to do something, right? That's one instruction. That means one cycle of a CPU instruction, the action the CPU can take. So 64-bit systems means it can at one shot change 64 bits in a memory sense. Well, that's like a rough approximation of that statement. So if you have, so in the past, we have a 16-bit system, we have 32-bit system. It always double. That means because the hardware is allowing the manipulation of one and zeros in a wider and wider range. So if you can do 64 one and zero manipulation at once, you can achieve more data like updates in a shorter period of time. So all the major operating system is now upgrading to 64. Like all the new computers you buy will be on the memory chip. So those target means you're going to target like 64-bit systems, and we have like a Linux here. We have also have linker and this is the compiler. So those things means like in Rust, because it's a system level language, target means you target different systems, right? You can target different memory chip. So ARM is actually a chip. So how many chip companies do you know? Intel and Intel is one. What else? Who produce CPUs? Which company produce CPUs? AMD, Intel, AMD for good for. They also do like video cards. What is other video cards? NVIDIA. Yeah. So ARM is also a CPU kind of architecture. So those things means what CPU you're using. So i60 6086 means a type of a CPU. So those means, so in a low level, right? Your programs are tied to your system, also tied to your CPU type. If you copy one file from Windows machine to a Mac machine, if you double click, will it run? If you copy an exe file to a Mac machine, or you copy like an app file from Apple machine to a Windows, or vice versa, do you expect it to run? No. Most likely it will not run. Like actually 100%. If you just do a copy from, if you copy a game from Windows, like you copy a whole folder or anything, you copy to a Mac machine, it will definitely not run because Mac is a different architecture. Like you have different CPU, have different operating system. So here the target means we are trying to produce the proper binary file or the proper target for that system and that operating system. So here is the example saying if you have different memory chips, you have different operating systems, you're going to use those compilers or called linkers to produce the targets properly. Otherwise, if you produce a different targets, it will not run on a system which is not the target. So here back to the mobile and the Rust point. So that's why we have to back to this diagram. So that's why on Android we're going to produce some kind of targets can run on Android. For iOS, we're going to produce some kind of target can run on iOS, which their code is the same, like more or less the same. It's written in Rust, like source language, but you need it to run on iOS or you need to run on Android. You need different compiling tools. You need different linkers. You need different tool chains to build them. So those two things talk about like what set of tools. For iOS, you need a bunch of like Apple's architecture. You need Apple's targets to produce like the binaries which could be understood by Apple. And you need some kind of glue code to make them work. Even the source code for Rust is the same, but they will produce different binaries to different systems. Questions or not really? But when we do the exercise, you guys will figure out. So next week we try to do this part of the exercise. We actually, depending on the system, we take different times. Okay, so that's that. And there are some wrappers or people already doing some kind of. So those other two links are actual open source project as like a boilerplate, as a framework, as like something you can start to looking at how other people trying to write the simplest code for allowing Rust run on Apple, Android, and other. So those are like developers trying to get like bootstrapping code for you to do something quick. So those purposes for allow Rust code to run on iOS or Android. So people develop some. This is the kind of the bootstrapping code. So for the local native project, I take inspiration or like basically see other people how they come up to glue the code together. Next piece we're talking about, we have 10 minutes. I'm going to talk about the Android Studio. So for Android, so Google owns the Android ecosystem. They produce this tool, which is Android Studio. So when you open up the source code for the Android in our application, it will show up like this. On the right, on the left, it's the source code. We will have a Java section. We have a resource section, RES section. So User interface we talk about, right? Still go back to our diagrams. Like this part, the user interface part, is defined in a kind of like in a graphic way. So in our mobile app, we have those different layouts. We have different views. So they are defined in here as XML files, but it's pretty much like a markup language. So containers within containers, you specify which container is inside which container. It basically will build a view look like this. So it has like a list inside, you have items inside, you can have like different components. So all of those correspond to some kind of, so this is a button, it corresponds to a button section. This is another button, this is a text view, show something, this is another fragment, or like this is another component. So here, this is in Android, you define a user interface, like just describe how the UI will look like. The code here is under like the Java section. So you see we have those code. We have different activities. We have different objects. So those things are manipulating your control user interactions. So you have those kind of functions called onActivity results. You have onClick events. So you click a button, what you do? You execute a function here, try to do something else. And most importantly for us, right, we have this Rust bridge. We have this system node library local native core. So this is where the Rust component is getting loaded into the Java system. So that's where the Java language or JVM language call into the Rust. So here we have one function called run, input a string, return a local native run, output as a string. So this is just a single function to wrap all the functionalities our Rust library provide by input a string, output a string. So what's the string contains? What the format of the text contains? Is that random string or is that some kind of structured text? Okay, we talk about JSON, right? JSON. So we also see the example of that. Right? So our string will be a well-structured string. It will have a structure. You cannot find a random string. You must be like this. You need to balance all the parentheses. You need to balance all the commas. And you need to have a specified format. So here, when we run this bridge, like when we call in from Java into Rust, here the string or the text need to conform to those formats. That's where the mobile to the Rust native part come together. So if you wire up all those components in the Android Studio, you can run it. And there are two modes you can run it. One is using an emulator. Emulator means it will open a simulator. It will open a fake device on your own computer. Other way is you have a cable you connect to your own device. You can run your application on your own device as a debugging thing. So if you're using Android, this will be your tools on that. And one other thing I want to let you know is we have this GNI libs. So here we have those we have different local native core.so files. So those are the reference for this library. Right? So here when we say system node library, it actually load one of those libraries depend on the prefix. The prefix is basically the architecture of your CPU. So different device, like Android has so many devices, right? Different Android devices have different CPU, different architecture. So when you run it, it will actually, so Rust produce multiple library, the local native core library for different targets. On a particular Android device, it will load the library which compatible with your device to when it says load library. If you have a different library, say you have a 64 library, but you load it on a 22 architecture device, it will crash. So here we also have this section is basically those are the reference to the target, the output of the SO files is the is a Rust is a Rust target we produce. So it's a device specific, it's architecture specific. So here we have like 4 different targets, 4 different SO files. They have the same name, but when you run a different device, it will pick one of them compatible to your target. Okay, so that's kind of an overview of the mobile part. Still have some time. I will talk about NDK piece for a while. So NDK is a native development kit. So this is only for Android. When we run something on Android, Android is different than Android itself is an operating system. It's different than iOS, different than Windows, or different than Mac OS. If you want to develop something like native on Android, you need to use these tools. So those tools are the linkers and compilers for the tool. So specifically, those means those linker files and the compiler files. So if you have a different architecture, you're going to use a different linker. So when we have like 4 different targets, you will have 4 different linkers for Android to actually produce those targets. That's kind of the NDK means. Then, and those are pretty much the same, kind of showing like you can install those in different locations. When we do the exercise, I will try to walk you through those. Those are the actual like compilers for different targets. They have similar names, but they are prefixed by like their architecture things. So last, talk about Java and not sure how to pronounce it. Kotlin. How will you pronounce this? K-O-T. Kotlin. Okay. So Java and Kotlin. So currently, those are both JVM languages. JVM is Java Virtual Machine. What does that mean? That means Java as a language, it runs on a virtual machine. What does that mean? That means you can have different language on the same Java virtual machines. So actually for our project, you see any of those .kt files is actually in Kotlin language. And the other they actually I converted all of them to KT. They look like Java, but they are a different syntax. So takeaway is the Java virtual machine can support multiple languages, and this Kotlin language is a kind of new language developed on the virtual machine. Why is it doing that? They're doing that because they introduce some features which is more user-friendly, or depends on your opinion, better for developers to not make mistakes, to correct some actions if you just use Java, or to reduce the code is introduce some useful conventions. The code become more concise and short, but they run on the same machines. So in our project, in this file, I think I convert most of the code to that. So in Android Studio, you actually also have some kind of they encourage you to convert your code into this new language to make it shorter, make it more concise. There are also other reasons like people trying to do this, but it's like so in JVM in Java like ecosystem there are many multiple other different languages. There are Scala, also like a Clojure, um, targeting the same JVM. So if you search, so that means the the Java ecosystem is actually pretty comprehensive because that's like the enterprise language. That's like the most, I will see the most money making language for the whole industry. So all the larger companies using Java extensively, they have more like more ecosystem and more languages developed on top of it. I think that's pretty much it is for today.